Hello everyone. Hello everyone. How are you doing today? Welcome to your channel promoting safety engineering. And today I want to talk to you about HAZOPs, about how to facilitate a HAZOP, the little intricacies that comes with it. So I'm going to jump right in and I'm going to explain. I already in my previous video I talked about how you mark up your nodes electronically, and this was kind of how I mark this up. Now you have to have a good knowledge of process engineering to be able to break up PNIDs into nodes. I'm going to have another should I say video for that, which I'll be explaining how to actually break it into nodes, not just mark it up. How you either go with the flow or the pressure regimes, or one of there are various ways you can break a set of PNIDs into nodes so that they are easily manageable and easily one can easily go through them with the HAZOP methodology. Now, let me just give a brief description. What is a HAZOP? A HAZOP is a short form. It's actually called a hazard and operability study. It's a structured and systematic examination of a complex, planned, or existing process or operation in order to identify and evaluate problems that may represent risks to personnel or equipment. The intention of performing a HAZOP is to review the design, to pick up design and engineering issues that may otherwise not have been found, and this is due to these issues could come about due to deviations from the design intent. So when you're looking at it, we're not just looking at hazards. It's not like a hazard, which is called a hazard identification process in full. This is a hazard. It's looking at the hazards that come out of operations. That when you're opening a valve or closing a valve or some maintenance work, or it highlights those issues so that you know that when this system is in operation, what are the that could come? Is this one going to be on? Is this pump going to be on standby? Is it going to be a hot standby? Is it cold standby? If it's operating, do you have a minimum recycle line so that your pump doesn't cavitate or overheat? You know, those kind of issues. That's what a HAZOP wants to pick up, amongst many other things. So I have a HAZOP that I've done, and I want to just break it down and explain how you go through the motions here. Uh, this is the so to do your HAZOP, you must have already brought in your the entire team. We should have your process engineers, your safety engineers, your operators, the HAZOP facilitator, the chairman, and the scribe. And then you could have different disciplines coming in and going, but those are the core disciplines that are required. Of course, you should have your instrumentation and control also, and then maybe mechanical could come in, civil could come in as needed. But really, you need your chairman, your scribe, and then your process engineer, your a safety engineer, and your instrumentation and control. Then the other and operators and the others could come in and go as needed. Now, before you start, the scribe should have set up the worksheet. You could use um, um, Microsoft Word, or you could use Excel, and they also specialized software which actually help you um, record your HAZOP process a little bit. They are more automated and reasonably user friendly. You can hit me up and I can give you a call, and I could send you an email with a few of the software which you could use for that. Um, Firstly, the scribe should have written everything necessary to on the spreadsheet, your what project it is, your node boundary. This is very important. Your node boundary here, saying where the node exactly starts from and where the ends are. When I'm going to do the video on nodes, I'm going to explain that, and the node should have a name. So this is around the HP separator, and then of course the dates. Then for that particular node, you have to describe the flow, the physical parameters, the pressure, the temperature, the composition, and also not just, it has to be the design and operating. So design and normal or design and operating. So design for whatever it is, and then the operating, and then the pressure, the design pressure, the operating pressure, the design temperature, operating pressure, and all that. And then the intention of the node should be clearly written out. This is to receive fluid from the HP wells, to separate the liquid from gas, and to transfer the gas. Now, and we are looking at normal operations. That's then, of course, the drawing numbers, the P and ID numbers that you're using, that you'll be that the nodes that have the nodes in them, and then the flow that you the parameter you're going to be looking at. Normally, you have parameters like flow. You also have um, pressure. Then you have level. You have temperature. Those are parameters that you use in the HAZOP. So the way the words are formed, so the process is supposed to operate in the normal way it's supposed to operate. So you look at the deviation, which would be a combination of the parameter and the guide word. So a deviation could be no flow. That's no flow from it's a no flow than from what is intended. So there was an intention that there would be flow, and now we're having a no flow, and it could be less flow. So there was an intention that we would have a certain amount of flow, that's 33 million scuff, and we are having less than that, or we are having no flow, or we are having other than flow, that's flow where there's not supposed to be flow, or we are having reverse flow. Reverse is going in the wrong direction than the design intent, or we could have more flow, more than 33 million scuff. And then also there's pressure. You could have more pressure, meaning we plan on having normal operating 32 bar, and then you're having, let's say, 36 bar. That is more pressure. What could lead to it? We could have less pressure, more pressure here, and we could have less pressure here. Also, we could have a vacuum, meaning there's nothing in there. And then you go to temperature, what could cause more temperature, what could cause less temperature. And so those are the guide words you use to critique the system, to critique the entire process flow, and know, okay, this is where we're going. So the design, the node intent is to receive fluid from HP wells and separate liquid from gas and transfer the gas. So this is where the flow is going to come in from the HP wells, HP production, you can see here, goes into this HP separator, and then the liquid will go out through the liquid leg and the gas will go out through the top. So that's, it splits. And so this separator does the job of splitting that flow into two, into liquid and into gas. There are some separators that also take out oil separately from liquid, and like oil from water, and then from gas. So those are three-phase separators. If you look at my video on separators, I explained a little bit more on that. So this is just a two-phase separator, meaning it takes in the flow from the HP production header and separates it into gas going out the top and liquid going out the bottom. Now that has been established, so the gas is supposed to be transferred, and that is what the HAZOP will be looking at, like what could actually cause this design intent to take liquid fluids from the wells and separate them and transport it. What could actually change that? What could actually cause a deviation from that design intent? And so we've looked at it, and now so with the first guide word normally in a HAZOP is should be flow, because we want to flow either fluids or gases or liquids or oil or water. We're always flowing something because that's what the whole process is about. So normally we start with flow. So we're saying what could be a cause of no flow within this node. So when you look at it, since you have to have an understanding of how PNIDs work, this is where the initial flow comes from. So if this valve, this is an SDV, if it fails in a closed position or if it's stuck closed, like what are the errors that could, a valve can fail in a closed position, or it can actually get stuck closed if it's not properly maintained, or for whatever reasons there's a loss of instrument air. For whatever reason, it could actually fail in a closed position. So when that happens, automatically you have no flow coming into the separator. So the HAZOP has picked that up. So SDV 101 upstream HP separator stuck in closed position. So that is the first deviation, and that is the first cause of no flow. So this SDV 101 is stuck in closed position, which doesn't allow fluid flow in here. And so that's the first cause of a no flow. And so what are the consequences? You look for at the consequences. The well would shut in because that stream here is coming directly from the wells. So that's the first cause, and it would lead to well shut in, leading to production deferment. Yep, so that's the first consequence. You could have as many consequences as are possible. You have a potential for pressure buildup upstream, the SDV. So of course, if this is closed and the line is trying to flow, there would be a potential pressure buildup inside the piping, and so that's the second consequence. And then the third consequence, starvation of gas turbines, meaning when we flow all this, the end point is actually to have gas going out the top to the gas turbines. Now, when this happens, is some of the gas that's flowing in here is supposed to use to run the gas turbines, and that doesn't happen. So you have a starvation of the gas turbines, and then also you have no liquid level in the vessel, meaning there's supposed to be a minimum level of liquid in the vessel. You wouldn't have that, and automatically that could lead to a gas blowby. So all those have been captured as consequences of the deviation. Now, what are the safeguards? What are the designs we've put in place to ensure that this doesn't happen? And after we look at the designs, also or the control measures you've put in place so that that doesn't happen, you also have to look at the what could you do to make the system better? How could you improve it? So we looked at, okay, so a PSV at the arrival manifold, meaning upstream this place, there's a PSV on that manifold. So if this is closed, the PSV would pop open and relieve to the flare. So that's a protection against overpressure in this line. Also, you have SSV at the wellhead, meaning the valve would shut in and would stop the well from producing, meaning you wouldn't have anything in this line. So that's a safeguard. Also, you can have another safeguard as your preventive maintenance, which I could write in here. So maintenance. So that's a protection, of course. Also, those are, and what we're just trying to say is that if this SDV is properly maintained, it shouldn't actually fail in a closed position. Also, you could have another, which is position markers, position indicators would show the position, the valve position in the control room. Now, I don't know if there's a provision for position indicators. So normally, if this valve is failed, if it's stuck in closed position or it's in open position, it should have a signal that goes to the control room telling the operator what position the valve is on. And then you would be able to actually say, okay, this is why it's not flowing, it's closed or it's open. So those are all safeguards. This doesn't actually do anything but just alert the operator that there is an issue with that valve. Now, it's always good to explain your safeguards properly so that whoever is reading the report and that wasn't in the workshop would actually fully understand what's happening. Also, then you could also rank it based on your risk matrix. I would have another video where I would explain what a risk matrix is. Um, so it's a way of analyzing the risks to know, okay, are we operating safely? Is this a risk that we can overlook, or is this a risk like it divides risks into um, low, medium, and high? And so this is high would be red, medium would be around yellow or orange, and then low would be green. So this is a medium risk. So we also said consider implementing a bypass around the SDV with a spare SDV. So meaning instead of having just one SDV here, why don't we have another line here with another SDV? So if this fails, we can open this SDV and run the process through the second SDV. So it's SDVs are very expensive, but if the um, if the process is actually very critical, you would want to do that. You could think of sparing it. So that is the first deviation. And then you go into the second thing that could lead to a no flow. Nothing here can cause that again because there's no other valve or there's no spec blind, there's no spade, there's no pump that could actually push the flow. And also remember in HAZOPs, the causes can come or must come from inside the node. But however, the protection can come from outside the node, the safeguards. You don't want a situation where you are thinking wildly and saying, okay, so what if a tree falls down on this pipe? Or what if someone comes and for some external force breaks open this pipe? You don't want to look at that in a hazard. That should be looked at in a hazard. You're looking at stuff that could come from operability. Now, you could have a pipe rupture if the line is not properly rated and you close a valve and the line is not rated to take that amount of pressure and the line could actually rupture, but not from external consequences, but from issues that arise inside this node. So the next that we looked at in the hazard is sorry about the noise coming in, is inadvertent closure of any manual valve across LV102 on the liquid outlet of HP separator. You have to explain it properly in the courses. So the liquid outlet of the HP separator is here, and we're looking at any of these manual valves is inadvertently closed, and that's if any of these valves is closed, that would mean you wouldn't have any flow of liquid out of the vessel. Now, so any of this manual valves is inadvertently closed, that would lead to no flow in the liquid leg. So that what are the consequences from that? That means there would be a liquid level buildup in the HP separator. Go back. So meaning no liquid evacuated from here, only gas. The liquid would actually start to rise up, rise up, rise up till the vessel is full, and you don't want that. That means you're having more level. So you have liquid level buildup in the HP separator, potential for liquid carryover to downstream equipment, meaning if the liquid continues rising, you could have liquid going into the gas lines. You don't want that. So you have to flag that up. And then potential damage to gas engine generators. If liquid goes all the way into the gas lines and ends up in the gas turbines, it could actually damage it. So what are the protections in place to the safeguards in place to actually stop that liquid, that's to actually pick it up if the any of those valves are closed? So you have a level alarm high, which would alert the operator. It's inside here. So you have a level alarm, which would actually tell the operator that the level in this vessel is getting too high. Then also you have a trip, a level trip high. So meaning after the level alarm and the operator, that means it alerts the operator in the control room and nothing is actually done. Then the level keeps on increasing and then you get to a level trip high, and that would actually automatically close this SDV. That would be looked at under cause and effects. So once that happens, that's called a trip. It would trip the SDV upstream the separator and it will close it, and then you would have no flow into the system. So that's a second protection to keep this from getting too filled up, because we don't want the worst case scenario, which is actually liquid getting into the gas lines. And then you also have your SOPs, which would ensure that the operators don't go here and inadvertently close them. So that is the protection. And then we've ranked it and said, okay, what are recommendations? Well, how could we actually make this process better? So consider installing an adequately sized flare knockout vessel, meaning if you have a liquid carryover all the way down into the flare system, you want it properly sized so that it can trap as much liquid as possible. So you have liquid going all the way into the flare lines, and then you want to ensure that they are actually properly sized. That's here. That means you want to make sure the vessel is properly sized to trap whatever liquid is coming in, and so you don't have liquid actually going to the flare stack, which is very, very dangerous. It could lead to a burning rain. And also confirm functionality of level switches on HP separators. So you want to actually be sure of the level switches here so that they are not closing the wrong SDVs. That's a recommendation. And also consider locking open the manual valves the across the LV102. So you could actually lock these manual valves open with a physical device, which we call it's a Lotto. We call it a Lotto system, which is lockout tag out. So you could actually lock them with the valves physically so that no one mistakenly goes there and opens them. So for you to actually open them, you'd have to get a PTW, that's a permit to work on those lines, from your supervisor. So that's a protection in place. Now, you could also have your LV102 stuck in closed position on liquid outlets. So this means your LV102 can be stuck in position, in closed position. So meaning maybe due to maintenance, loss of instrument, air, a bad valve, whatever, you could have this filling in a closed position and you wouldn't have any liquid. So this could be open, this could be open, and this would be closed, and you wouldn't have any liquid flowing out, which would lead to the same consequences which we had above, and would kind of have the same protections, but also your preventive maintenance would help with your LV not messing up or answering when it's on demand. Now, of course, now you after looking at the liquid leg, you go to the gas leg. And so what could be a cause of no flow here? This valve could actually be fail in a closed position, or this valve could fail in a closed position, or these valves across could be inadvertently closed, and which could lead to inadvertent closure of manual valves across PV 103 on gas outlets. That's PV 103. That's here. So any of these manual valves across fail in closed position. And then you have flaring, meaning the flare lines would have to open up, the logic would open it up, and you just have increased flaring. Potential for pressure buildup in vessels. So meaning if this closes temporarily or momentarily, you would see a pressure spike up in this vessel. And then also you could have loss of fuel gas leading to plant shutdowns. Yes, so because these lines send gas to the fuel gas system and the gas turbines, and not having gas there could actually lead to the entire plant shutting down. And so what are the protections? You put a trip, you put a PSV. If you the PSV would protect against these are PSVs here, protect against pressure buildup in this vessel so you don't have a vessel rupture. They are your last line of defense. You could have your pressure trip, so if the pressure gets too high, you close the inlets of the vessel. And so you just get creative and come up with good recommendations. You could lock open the valves, although most times you want to lock open when it actually has a safety consequence, because you don't want to always keep getting PTWs to carry out little minute tasks which should be mundane and the operator should already be trained to handle. So you have all that. There's a lot more, and then also you could have less flow. What could lead to less flow? The PSVs might be passing, meaning they weren't properly maintained, and you'd have flow going through the flare, and which would cause less flow in your intended direction. You could have leakage of lines, flanges, fittings, which could be bad because lead to fire and explosions, or it could lead to environmental pollution. So you definitely want to avoid that. So you have to make sure everything is properly maintained. Uh, you could have your manual blow down valve inadvertently opened on that line, and that would also lead. That's this, and that could lead to. So if these valves are inadvertently open, you don't want that happening because everything, all the gas would just be going to the flare. You could have more flow, meaning if any of these level separators, like if any of these um, pressure control valves fails in open position, you wouldn't have any control over this process because they are all at set pressures which they open or close based on what's happening to the other, um, based on the what the logic solver is telling them to do. Now you have one that's actually no longer listening to the logic controller, and it's just stuck in open position. You have so much going out, and that could lead to a vessel imploding, or there's so many other consequences. So that would be a more flow in wrong direction, or you could call it a misdirected flow. It depends on what you all agree on, because a HAZOP is a combination of all the experiences of everyone in the team. So it depends on who is and who are in the HAZOP to give you a good HAZOP. So you can have people who don't really know about the process HAZOP in it, because then it you wouldn't come out with good recommendations, because for whatever reasons your recommendations are have to bring risks to a lap. You don't want to implement a very expensive solution which the client is not willing to embark on. So you need people who know about the process around. So you, after looking at flow, you go to pressure. After looking at what could give you more pressure, what could give you less pressure, and then you go to temperature, what could give you more temperature, what could give you less temperature, and you have composition, so many other parameters that you look at. So all in all, that's the explanation I wanted to give you on carrying out a HAZOP. If you have a good idea of process engineering, that should you should be pretty good with this, and you could HAZOP almost any kind of system to get your to make the process better. Anyway, thank you very much. Do have a lovely day. It's Toby Sheon once again from Promoting Safety Engineering. Thank you. Have a lovely day. Bye bye.